All right, so last class we talked about how mass changes when we break up components in a nucleus or if we add components together. I think that's what we talked about. Anyway, we're talking about it now. So consider if we form helium-4 from its components, just looking at the nucleus. So if we're looking at the nucleus, helium-4 contains 2 protons and 2 neutrons. We're representing protons as helium here. Maybe we're also including the electrons in there. It doesn't really matter. If we add up those components, 2 heliums, helium-1s, is going to have 2 times this many AMUs, and our 2 neutrons are going to have slightly more mass. And if we add that all up, we get a total mass of our components of 4.03298 AMUs. If we look at our product, if we look at the helium nucleus as it actually exists, the mass measurement that we get is 4.00260 AMUs. So there's a difference in mass of bonded versus unbonded components. And this is what we call the mass defect. That's going to exist in all stable nuclei. And bonded here, we're not talking about like covalent bonds, just them being stuck together, glued together with atomic glue. And the mass is going to be less than what we expect, at least in this case. So what does that have to do with anything? The energy corresponding to the mass defect is called the nuclear binding energy. So it's the amount of energy that is holding the nucleons together. The nucleons are the components of a nucleus. And typically, since we're talking about really small particles, they have very small masses. They also have very small amounts of energy associated with them. Typically, we use this new unit called an electron volt to report that energy. And an electron volt is the kinetic energy of an electron that's been accelerated through a potential difference of 1 volt. So if you take 2 charged plates and you apply a voltage difference across the 2 of them of 1 volt, and you send an electron zipping from one plate to the other plate, the amount of energy that that electron has is 1 electron volt. And as you might imagine, a tiny little particle flying through space is going to carry a small amount of energy, but it gets us down into the range that we're working with here. Energy of an electron at 1 volt potential difference. We can also represent it as mega electron volts. So add our mega prefix, mega being bigger than kilo. And it's a very small number of joules. We can also relate an AMU to mega electron volts. And this is probably more helpful for thinking about our nuclear binding energies. These are both conversion factors that I would give you on an exam. So this is helpful for relating the amount of energy to a mass. For example, the mass defect for helium 4 is 0.03038 AMUs. What is the nuclear binding energy? Well, it's related to the mass defect. And we can actually use this AMU to mega electron volts to do that conversion. So 0.03038 AMU, our conversion factor 931.5 mega electron volts per 1 AMU. This will give us a value in mega electron volts. If we wanted to, we could also convert it over then to joules. .03038 times 931.5. The nuclear binding energy is 28.29897 mega electron volts. We'd probably round that off at 28.30 mega electron volts, which is a number that doesn't really mean anything to us because we don't have experience with electron volts, but I think most of us probably don't have experience with joules either, so that also doesn't really mean very much. So we might as well just leave it in mega electron volts. One of the reasons that this is useful to calculate is that it lets us compare different nuclides. Different nuclides have different mass defects. So different nuclides have different mass defects, and because they have different mass defects, these mass defects correspond to the nuclear binding energy. And so we can measure how stable a nuclide is based on these mass defects. For example, we can calculate the mass defect and nuclear binding energy per nucleon in mega electron volts for uranium-238, which has a mass of this value. So we're going to calculate mass defect and nuclear binding energy per nucleon in mega electron volts for U-238, which has a mass given there. Something that we're going to need for this is the mass of a proton or the mass of a neutron. We'll need both of those. So let's go back earlier in the slides where we have those. So we're going to be using this 1.00789 and the 866. I said 789, 783. And 866. Okay, so those are the values in AMUs for our protons and for our neutrons. How many protons do we have in uranium-238? No. 118 is the maximum number of protons for elements that we know of. 118 is oganesson.
That's for uranium?
We're looking at uranium-238.
92.
It's 92. So the periodic table, we find the number. It's usually listed above the symbol, the atomic number, it's 92. And then our number of neutrons is just the difference. So 238 is the mass number for this particular nuclide. And it equals protons plus neutrons. we know the number of protons is 92, so we can figure out the number of neutrons. So 238 minus 92, that'll give us the number of neutrons that we have, which is 146. So we've got 92 protons, 146 neutrons. We'll multiply 92 by the AMUs for a proton. (92.72036), and we'll do the same thing for our neutrons, which gives us 147.26436. And then we add those two things together. So what we're calculating here is the predicted atomic mass of uranium-238, or just what the components weigh. But then after we glue them all together, to actually make uranium-238, we discover that it's 238.050784 AMUs. So it's lost some. That difference is the mass defect. Do we have questions so far? Okay, so calculating mass defect. I'm going to call it components, the nucleons, the protons, the neutrons, their sum mass, minus our actual mass. That's the calculation we're doing. So 239.98472 minus the value we were given of 238.05 and the rest, with units of AMUs. So our mass defect is 1.93394 AMUs, assuming we did this correctly. And then to calculate the nuclear binding energy per nucleon, we can use this 931.5 mega electron volts equals 1 AMU. (931.5). So it's 1801.46511 mega electron volts. And then, to make it per nucleon, we just divide by the number of nucleons that we have. How many nucleons do we have? It's 238. So we divide by 238. So it's 7.57, if we round it for 3 sig figs, mega electron volts per nucleon. We'd probably round it for more sig figs, but I don't want to write all the numbers. The reason that we would express this in per nucleon is because if we've got larger nuclides, like with uranium-238, that's relatively large, because we've got so many nucleons, we're going to have a larger mass defect. We're also going to therefore have a larger total nuclear binding energy. So if we express it in a per nucleon fashion, then that lets us compare to things that are smaller as well, rather than just talking about the total amount. The amount per nucleon gives us a comparable amount. This is a curve of binding energy, a graph of binding energy. So on the y-axis, we're looking at the binding energy per nucleon in mega electron volts. That's so that our numbers are comparable. And then on the x-axis, we've got mass number. And generally what we see is that we've got a very low binding energy per nucleon in mega electron volts for deuterium, which is hydrogen with proton or with one neutron. And the binding energy per nucleon increases as we get up into this range around 60. A is our symbol for mass number. Just kind of in this general region. If we get above that number, our binding energy per nucleon starts to drop off a little bit. What this means is that if we react nuclides together, these lower mass nuclides are going to have a tendency to fuse. They're going to combine together to increase their binding energy. And these things that are bigger are going to tend to break into smaller bits, which also increases their binding energy. And that's what this fusion and fission label are. So if we're bigger than around A equals 60, we expect fission. We expect that if we collide two particles together, they're going to break apart. Or if we hit them with a neutron or something like that. If we're smaller than around A equals 60, then we expect fusion. It's actually beneficial to include a new nucleon or many new nucleons into the nucleus. It increases the binding energy per nucleon, and it's more stable. Say that again?
So when, like, the less they bind, the more the energy?
The smaller they are, the more they're likely to bind together?
Yeah, well, because you're saying that, like, uranium and barium create fission, and those
Yeah.
are not binding, right? So that means they create more energy when they're not binding as much as, like, the smaller elements?
They'll release energy when you break them apart. So when uranium-235 and barium-139 undergo fission, they release energy because they're becoming more stable. They're decreasing their energy by increasing their nuclear binding energy. In fusion, I believe it's deuterium and tritium that get reacted together, which I expect tritium would also be really way down here. So those are going to have like the lowest binding energy per nucleon, and then they would scoot up to somewhere like they produce regular helium-4. That's going to be a huge increase in their binding energy, so it's going to produce a lot of energy. Part of why fusion creates like 1,000 times more energy density than fission. So nuclear fusion is our combination of two light nuclei to form a heavier one. Nuclear fission, on the other hand, is splitting a heavy nucleus to form two or more lighter ones. They're both highly exothermic because of this change in binding energy per nucleon. And fusion is the energy source of stars. That's typically what's happening inside of stars. The reason that we haven't used fusion yet as an energy source is because it releases too much energy for us to handle. So the hydrogen bomb, a fusion bomb, has up to 1,000 times the explosive force of an atomic bomb, a fission bomb, which I believe we've talked about previously in this class. Not fusion, sorry, fission. So deuterium and tritium, two isotopes of hydrogen, react to form helium and a neutron. In order to start a fusion bomb, you have to set off a fission bomb. That's the sort of energy that it takes to get it started. In most of the trials, almost all of the trials to try to use fusion to produce energy in a nuclear reactor, the amount of energy that's gone into the reaction, just getting it started, has been more than the energy that we've been able to get out. Not all of them, but most of them. So nuclear fusion's ideal for a couple of reasons. It's got much higher energy density than fission, and it's got much less problematic products. We actually need more helium. You may not be aware of this, but helium, the thing that's in like party balloons, is light enough that it just escapes from the atmosphere. So when it gets out of the reserves in the ground, it pops out of the party balloon. You breathe it out because you're doing your fun party trick where your voice goes up. It gets out in the atmosphere and it's light enough that it just escapes out into space. And so we're slowly running out of helium, which is problematic because we use it to like cool MRI machines. And so if we run out of helium, that kind of throws a wrench in running MRI machines, or it'll become much more expensive. However, the main problem, is that nothing can withstand the extreme temperatures. So we're talking about millions of degrees of temperature that are produced. So literally every substance that we know of will melt, or just evaporate or disintegrate at those temperatures. So the way that they control that high temperature that's needed for fusion, is that they have magnetic coils. And so they use magnetic fields to try to control and keep that fusion occurring, to push those ionized particles and keep them in a nice narrow band in the generator so that it doesn't touch anything and instantly melt it. Which is different from fission, where you can just cool it with water and the water turns into steam. In the Middle Ages, alchemists wanted to transform low-cost metals like lead into gold. They were not successful, since elements retain their identity in chemical reactions. So you can't just like do a chemical reaction and poof, suddenly you've got gold. All of your atoms are going to stay the atoms that they are. However, if we undergo nuclear reactions can change the identity of elements. So nuclear reactions change element identities. We can actually turn something from one element into another element. So the thing that alchemists were very eager to do, trying to turn lead into gold, or just anything that's cheaper than gold into gold, we can actually do that. It's just not cost effective. There's no point in doing it. So in radioactive decay, in fission, and in fusion, transmutation occurs. We're mutating our element into something else. There's some other nuclear reactions that can result in transmutation. So reacting nitrogen with helium, you can produce oxygen and hydrogen and other sort of like atom smashing reactions. Those sort of atom smashing reactions occur in things like particle accelerators. So we're going to talk about a couple of types of particle accelerators. In the 1930s, scientists began building devices that accelerate particles to high velocities. And if you're thinking high velocities here, meaning like thousands of miles per hour, we're talking way faster than thousands of miles per hour. So high is a little bit of an understatement here. And accelerating these particles so quickly makes more of these transmutation reactions possible. The faster that you run these particles into each other, the more likely something's going to happen. In a single stage linear accelerator, you're just accelerating a particle in a line. You're just shooting a particle. So you could take a charged particle and accelerate it by a potential difference. So basically, like the rough idea here is pushing an ion with a magnetic field. So you generate a charged particle, and then you apply a really large magnetic field behind it to basically shoot it like a bullet in this linear accelerator. And since it's a single stage, you just accelerate it one time. You might also have like the opposite magnetic field on the other side, so you're pushing it away at the same time that you're pulling it from the other side. The Stanford Linear Accelerator, another type of linear accelerator, is a multi-stage accelerator. So rather than having a single acceleration phase, it's like we're adding multiple of those single stages together. And you can get up to 90% of the speed of light. So that's like, I think that's 30 million meters per second. We'll do a conversion to miles per hour. $30 million meters per second to miles per hour, since we're Americans. All right, so the miles per hour equivalent, to give you an idea, is 67 million miles per hour. So that's the sort of speed that we're talking about, unfathomably large amount of speed. When these particles collide with a target or they collide with another particle, it produces subatomic particles that can be studied. So researchers using the Stanford Linear Accelerator won the 1990 Nobel Prize in Physics for discovering that protons and neutrons are composed of smaller particles called quarks. So they're not actually the smallest that they can get. You can break them into smaller pieces. You can build them with quarks. So here's a diagram of what that multi-stage linear accelerator might look like. We've got a vacuum pump. The vacuum pump's important because if you just tried to run this in like regular air, regular space, there's a bunch of particles. Like, it doesn't feel like there's a lot of particles to us, but if you try to shoot something at 90% of the speed of light, it's going to run into like hundreds of thousands of particles along the way, and that really slows things down. And so you have a very powerful series of vacuum pumps to try to get as much of the particles, the air particles, the stuff you don't care about, out of this tube that you're working in. And then you take a series of magnets, essentially. And so you start with your proton source, you accelerate it towards phase one, and then as it gets to phase one, you switch the polarity on your voltage source. So now phase one, instead of attracting it is repelling it. And phase 2 would be attracting it. So then it's accelerating from 1 to 2. You switch it again, it accelerates from 2 to 3. It accelerates again from 3 to 4. And you're just alternating it repeatedly to get it to keep accelerating. So you pull proton to 1. Then switch to repel proton from 1 to 2, etc. And the reason that these phases get longer is because the particle is traveling at a higher speed, presumably. And then you just run it into this target at the end. So that's the sort of stuff that might go on in a multi-stage accelerator. You can also use a cyclotron. I'm not sure what the tron part is, but the cyclo seems to be, right, like cyclical. So in a cyclotron, you've got two halves. So instead of doing it in a straight line, you've got, we're making it into a circle, essentially. So we take a charged particle, and you start it out in the middle, and then you run it around this track. And it's the same idea. We're alternating positive and negative, and basically like getting it to whip around, moving faster and faster. And then as it accelerates, it moves further out in this evacuated chamber until it hits the target that we have at the outside of our chamber. Questions about accelerators? I don't know that much. It's kind of just what's on the slides. You can always spitball, though. All right, acute radiation damage. Acute being short term. So like the amount of radiation damage that you'd get in like 5 minutes or an hour, rather than the amount that you'd get over a week or a month. So acute radiation damage results from large amounts of radiation in a short amount of time. The main sources where you'd experience acute radiation damage if you were around, for some reason, a nuclear bomb explosion, or if you were around an exposed nuclear reactor core, or you were just working in a nuclear plant and you happened to fall into a tub of nuclear waste, maybe. Those are sort of the places that you would experience acute radiation damage. You are very unlikely to encounter this. If you were exposed to one of these sources, however, you'd have a lot of your cells die. Most notably, things in your immune system and your intestinal lining. And so that results in a weakened immune system because of that immune system dying off, and an inability to absorb nutrients because your intestinal lining is responsible for absorbing nutrients. So likely, if you had a mild case, you might be able to recover, but death would be likely in more extreme cases. Things that you're more likely to encounter, but still unlikely to encounter, is increased cancer risk from long-term exposure. So lower doses of radiation over long periods of time can increase your cancer risk. The radiation can damage your DNA and other cells. So radiation, right, alpha, beta, gamma, all those sorts of radiation, some of those will penetrate your body and then happen to run into cells in your body. And it's possible they hit DNA, and maybe it causes the DNA to break, or it changes one of the bases, and maybe your body doesn't catch it when it's going to replicate that DNA. And so then it creates a coding error, and then possibly it does nothing, but possibly it produces a cancer cell. So normally it's going to kill the affected cell, or your body has mechanisms to say, hey, this isn't functioning as it should be. We're just going to not use that cell. Go ahead and undergo apoptosis. So that can cause your cells to grow abnormally and become cancerous if it's not caught. But a lot of the time your body is going to catch it. So your cancer risk is going to increase with, cancer risk is going to increase with increasing radiation exposure, but there's not really an exact threshold. So like less radiation is better. It's a little bit like lead poisoning. Like you could probably have a little bit of lead in your diet, like as a treat. But you don't want to have too much because ultimately it's bad for you. Like having a little bit of lead is probably not that bad. Like if you drink lead-infused water one time, you're probably not going to die, but it's not great for you, versus if you drink it a lot, like that's definitely worse. And radiation is a similar case. It's just better to be exposed to less radiation. Radiation can also cause genetic defects in future generations. It can affect the DNA in egg or sperm, and then that can cause genetic abnormalities if it's not caught. And we can see those in humans in places that have been exposed to large amounts of radiation. The way that we measure radiation exposure, there's, I think, 3 different classes of units for radiation exposure. So we can measure it as the number of decay events. So a Curie measures the number of decay events per second. So the Curie, and there's a couple of other ones that are analogous to a Curie, measure how many decay events a nucleus is undergoing in a period of time. But this is not an effective measure of how much biological tissue damage you're receiving, because the amount of radiation that's being produced doesn't correlate one-to-one with how much damage you're receiving. And there's different types of radiation that produce different types of effects. You could sort of think of it as like if the radiation types are like different boxers, right? Our alpha particle, that's going to be our prime Mike Tyson. He's going to hit you really hard, former heavyweight champion of the world, Iron Mike. Versus if you just get like a regular person, that's going to be more like your beta. And then if you get a little baby, that's going to be your gamma rays, right? So like taking 1,000 punches from a baby, most of us could probably handle that. 1,000 punches from a normal person would probably knock us down, and 1,000 punches from primetime Iron Mike Tyson is probably going to kill us. Right, so just talking about the number of punches you receive, that's like the number of decay events, it doesn't really correlate to the amount of damage that would be received. So a better way that we could measure radiation is dose, or measure radiation dose. Is to measure radiation dose. And that's the amount of energy, like in joules, that's absorbed by your body tissue. And these don't really correlate exactly one-to-one. So a gray and a rad, radiation absorbed dose, rads are the units in fallout. A gray or a rad are a number of joules per kilogram body tissue. So energy received by the radiation. Which is, of course, different than just the number of decay events. Because different decay events are going to produce different amounts of energy. It also depends on how far away from the radiation source you are, the amount of energy that you receive. There's also differences, so measuring the energy absorbed doesn't account for the amount of damage. Since gamma rays are low in ionization density, alpha rays are high in ionization energy due to their differences in penetrating power and the size of the particles. And so this is that third unit that I was talking about, the biological effectiveness factor. This is a correction factor that converts us into REM or other similar units. So I think the Roentgen is a unit of decay as well. So if you take your dose in rads, joules per kilogram body weight, and then you multiply by your relative biological effectiveness factor, this will give you your dose in rems. And this rems is the number that would be more important for thinking about how much damage you actually receive. So REM, not the sleep, is a better metric for the damage your cells endure or your body receives. And here's a table of a bunch of different radiation sources. So some sources of natural radiation. If you go on a 5-hour jet airplane ride, which makes it sound like it's for fun and not just like to go see family over vacation or not fun reasons, I don't know. You might get 2.5 millirem per trip. Cosmic radiation just from outer space, you'd maybe get 27 millirem per year. So just normal living your regular life, assuming that you don't live under a concrete dome the entire time, you're likely to experience something like 27 millirem in a year. From the Earth, terrestrial radiation, you'll get a similar amount. Natural radionuclides in your body give you even more, 35 millirem per year. Carbon-14 and other things that you just ingest as part of your normal life. And then radon gas, wherever that exists, 200 millirem per year as a lung dose. Presumably it's just around us. I don't actually know, I didn't look into it. If you go in for some diagnostic medical procedures, things like dental x-rays will give you 30 or 80 millirem. And so part of the reason that like dental techs step out of the room when they do your x-rays, when they press the button to make the thing go beep, right, is because they would also be exposed to part of this millirem, and since they're pressing that button a lot every single day, they would be exposed to a lot more radiation. So that procedure was developed because dental techs were getting cancer at a higher rate from just being exposed to those x-ray sources kind of secondhand. And there's some other stuff in there if you're interested in reading it. It takes a lot more than the average natural radiation dose. That's spelled wrong. It takes a lot more than what you would be exposed to in normal medical procedures or in just regular daily life for you to get a measurable, significant health effect. So that previous table was millirems. And the approximate measurement for an instantaneous radiation dose, if you get 20 to 100 rem, then you'll start to see things like decreased white blood cell count and possible risk of cancer increase. If you get exposed to really large amounts, you just die. But you would have to be exposed to a lot more than what we saw in that previous table in millirems. I think the estimate that is in another set of slides is like your annual exposure is like a third of a rem. Anyone want to guess what time scale that is? A year. Third of a rem per year. So the normal amount that you're exposed to on average probably in a year, you'd have to be exposed to way more than that, right? Like 60 times more than you get exposed to in a year in a single moment to start to see some measurable health effects. So radiation generally not something that you should be concerned about. In medicine, radiation is very helpful. So some diagnostic techniques involving things like radio tracers. You can take a radioactive nuclide, just anything that's radioactive that produces like beta or gamma rays, You can attach that to a compound or introduce it into the body directly, and then use very expensive instrumentation to watch where it goes in your body. Different compounds / tracers go different places and do different things. Tracers are great because you can detect them with great sensitivity, and they're identical in chemical behavior to their non-radioactive counterparts. I think we're going to talk about one of the examples. Yes, here it is, thyroid gland. So your thyroid cells naturally concentrate iodine. So they pick up / accumulate iodine. So if you have iodine in your body, that naturally gets picked up, uptaken by your thyroid cells. If you put in radioactive iodine, because your body doesn't know the difference between the different nuclides, that will also accumulate in your thyroid. So you'll have a radioactive hotspot at the thyroid. And this might be good for a couple of reasons. You might want to check how well is your thyroid taking up iodine in the body, so you inject somebody with some radioactive iodine, and you just kind of watch their body work over time and see how quickly that's taken out of the rest of the body and concentrated into the thyroid cells. The other thing that you can use this for is if you get thyroid cancer, then they can take out your cancerous thyroid. And if you've got any thyroid cells anywhere in your body, they just give you a dose of radioactive iodine, a larger dose. That's going to get picked up by the thyroid cells that might be floating around in your body and are cancerous, and then it'll kill them because of the radioactivity inside of it. So it's a very effective treatment for thyroid cancer. And then you don't have to go searching throughout the body, where are all the thyroid cells hiding? You can just inject the radioactive thyroid or radioactive iodine, and boom, thyroid cells are dead. And usually when you're getting these sort of treatments, it's small amounts. So different elements are taken up preferentially by different organs. You can use them to image organs, bones, arteries, or to locate infections or cancer. And here's a list of some nuclides, the type of emission that they have, their half-lives, and the body part that's studied. So I-131 is for studying the thyroid, and it's got a half-life of about 8 days. So it's not in your body for too terribly long. You can also tag antibodies with things like Tec-99. And those will gather at the site of an infection because they're on antibodies. Antibodies are going to gather at the site of the infection. So if they've got the technetium-99 with them, you'll see that signature wherever the infection is. You can also, in fancier studies, you can also use radio-labeled I guess this would also be antibodies, but can use other radio-labeled monoclonal antibodies. So the cool thing about antibodies and monoclonal antibody treatments is that they're extremely specific if they're well designed, which anything that you're going to put in your body is going to be extremely well designed. And so they will go to whatever site they're designed to go to, and they will only go to that site. They'll only bind to that particular whatever it is that they're designed to do. And the radio-labeled part, it just kind of tags along for the ride. So you can use the extreme specificity of monoclonal antibodies along with a radio label to figure out exactly where a sort of infection is or a particular target site for those antibodies might be lurking in your body. You can also use positron emission tomography. So you can take radioactive fluorine, F18, attach them to things like glucose, and then as that F18 decays, it'll emit positrons that combine with nearby electrons, and you can look at the energy that's released when those antiparticles annihilate each other. So it's going to produce gamma rays, and so then you can use a machine that detects gamma ray emission in your PET machine. A lot of the how we use this in medicine stuff is kind of just like an FYI, kind of a cool applications of what we've been learning about. Radiation like gamma rays are also very effective for killing internal tumors. So you can take gamma rays and target them at a particular part in your body where you know you've got cancer cells, and then they rotate those beams so that they're always pointing at that one spot inside of you, but they're passing through at different points. So you're spreading the damage to the other tissue while always focusing on that one part that's bad or unhealthy. That's why they move in this circular path. And you're often, with this, going to develop symptoms of radiation sickness, like you're on chemo. And even if they give you a therapeutic dose of like 100 rem, if that increases your cancer risk by 1%, that's probably worth it if it means killing the cancer that you already have, right? The cancer that you have is worse than the cancer that you might have, hopefully. So if you're definitely going to die from cancer, and they're going to kill that cancer, but also maybe give you a different cancer, usually that's going to be worth it, assuming that you don't go bankrupt and then also get cancer. Like, that's double losing. Could happen. Hopefully it doesn't happen. The other way that we can use radioactivity is to kill microorganisms, not just microorganisms. You can also kills bugs, or it can be used to kill bugs. We don't really use that in the US because people are scared of radioactivity. In the EU, they use this more than us. So you can use it for things like sterilizing implantable medical devices. Just hit it with a bunch of gamma rays. You can kill bacteria and parasites in food, like in meat and poultry. You can also use it to sterilize like salt. There are some salts that are like, this was not treated with radioactivity, and that's a selling point. I'm like, no, please treat it with radioactivity. I won't pay you more, but it'll make me feel a little better. You can also use it as part of controlling populations of harmful insects. So you can release sterilized fruit flies and then release them, and then they go on and try to make the next generation of fruit flies, but they can't, and so they're just kind of wasting everyone's time, and so then you get less fruit flies produced. In our area, this is done with mosquitoes. And I think there's an E in mosquitoes. So you make it so that they can't reproduce. So you like destroy their reproductive organs, or you kill their reproductive cells with a specifically targeted dose of radiation. So the point in sterilizing the fruit flies is that then when they go on to try to reproduce, they can't. And so then instead of producing another whole swarm of fruit flies, they're not doing that. It's just kind of reducing the number of fruit flies that can be produced because there's now all these sterile fruit flies out there in the environment. So there are labs, there are companies, there are groups that like a big part of their thing is that they raise fruit flies or they raise mosquitoes, like tons of them, and they're all sterile, and then they go and release them out into the wild. I think for mosquitoes, I think they just use sterile male mosquitoes, since I think it's the female ones that bite you. Because it would kind of suck if they were out there releasing a bunch of female mosquitoes and then everyone's getting bitten more, but like it would help in the, it's the whole thing. Anyway, that's all we've got for chapter 21. Any questions before we end?
I mean, I don't know if this has really has anything to do with the chemistry, but like fruit flies are part of like the decomposition for environment, so wouldn't that kind of affect that? Like sterilizing them?
I don't think the effect on fruit flies is big enough, like by releasing sterile fruit flies. I don't think it's big enough that it's going to affect like decomposition of things. This is probably more in an agricultural setting where this would be occurring.